Hello, this is Difficulty Math, and in this video we're gonna solve this integral, the integral from 0 to infinity of 3x minus 2x cubed over x to the fourth minus 7x squared plus 3 in parentheses plus 6x minus 4x cubed in parentheses squared. Alright, so we're gonna solve this integral, and so let's go to the first slide of our solution. And here we're going to use a little bit of residual theorem, contour integration stuff. So let's consider the function f of z is equal to 1 over z to the fourth power plus 4z cubed plus 7z squared plus 6z plus 3. And the contour, the path gamma is equal to, the path gamma is r times e to the it for t from 0 to pi over 2. So it's basically this quarter circle arc in the quadrant 1 from t equals 0 to t equals pi over 2. Alright, with radius r, because r times e to the it, so radius r. And the contour c is this whole thing here. And the first part here is basically a line segment from 0 to r on the real axis. And then we go along the quarter circle arc in the quadrant 1, and well, I forgot to mention that it's going up this way. So it's from t equals 0 to t equals pi over 2. It's going up that way because the direction is also important. And then the last part here is I times r minus t for t from 0 to r. So when you plug in t equals 0, you get ir. When you plug in t equals r, you get I times 0, which is 0. So here it is a vertical line on the imaginary axis going down from IR to 0. Alright, so let's get back to our original question and original integral. So here basically the path we're using is this quarter circle contour. The contour we're using is this quarter circle contour in the quadrant 1. It's going from 0 to r and then going up towards along this quarter circle arc and then going down like this. So here is IR. Alright, so this is the contour that we're using. Alright, so this is the contour we're using. And the reason why I chose that function is because, well, you should know that there is this formula, not really a formula, but like just a computation of division of complex numbers. So when we have 1 over a plus ib, you can multiply both the numerator and the denominator by a minus minus ib. Then we get that is equal to a minus ib over a squared plus b squared. Alright, and well, if we take the negative of the imaginary part, we're gonna get b over a squared plus b squared. And our integrand here is something similar to that form, not exactly but similar, because here this is our a and this is our b, and the thing in the numerator is not exactly the same as b, but it's b divided by 2, because the b here is 6x minus 4x cubed. When we divide it by 2, we get 3x minus 2x cubed. So our integrand is something of that form, of the form b over a squared plus b squared. So that's why let's consider something of the form 1 over a plus ib. So again, a is this and b is this. So we're going to consider something of the form 1 over a plus ib. Alright, so that is 1 over that whole thing, x to the fourth minus 7x squared plus 3 plus ib, and b is 6x minus 4x cubed. Alright, and if you look here, you see that x to the fourth is x to the fourth, because I to the fourth power is 1, and x squared is ix in parentheses squared, because I squared is -1. And then we have plus 3 and plus, well, 6 times ix. And then, well, I cubed is -I, so that is plus 4 times ix in parentheses cubed, because I cubed is minus I, so that's why we have minus I times 4x cubed here. Right, so that's why I chose that function, like 1 over that whole polynomial. And when we substitute z equals ix, like just choose that function f of z, and when we substitute z to ix, then we get this thing. And so that's why I chose the quarter circle contour, because when I choose this quarter circle contour, when we deal with the integral along the positive imaginary axis, we will substitute z to iz, and we will get what we want. So for the integrand, so well, let's move on with our solution here. So basically choose this function and this contour. And so we have the contour integral of f of z dz along the contour c is equal to the integral from 0 to r of f of z dz plus the integral along the arc gamma, the quarter circle arc, f of z dz, and then minus the integral from 0 to ir of f of z dz. We do minus because along the contour we go down from ir to 0. So it's the opposite direction. So we go down from ir to 0. So it's minus the integral from 0 to ir. And then for this third integral here, we substitute z to iz. So dz will become I times dz. And so we get that third integral is going to be equal to I times the integral from 0 to r of f of iz dz. So, well, after substituting z to iz, the boundary is gonna change from 0 to ir to 0 to r. And well, so notice that the limit as r approaches infinity of the integral of f of z dz along the quarter circle arc gamma is 0, because for any rational function with the degree in the numerator being at least 2 degrees smaller than the degree in the denominator, then the limit as r approaches infinity of the integral of f of z dz along the arc gamma is equal to 0. And here the degree of the numerator is 0 and the degree of the denominator is 4, so it's way more than just 2 degrees smaller. So that limit is 0. And so taking the limit as r approaches infinity of both sides, this is what we get. So we get this. So the contour integral of f of z dz along the contour c is equal to the integral of from 0 to infinity of f of z dz minus I times the integral from 0 to infinity of f of iz dz, because we're taking the limit as r approaches infinity, so the integral from 0 to r becomes the integral from 0 to infinity. Alright, and well, for the function f of z, you can find the zeros of the denominator of f of z, and you can find the poles of f of z, and you can verify that f of z has no pole inside the contour c. No pole inside the contour c. And so that means the contour integral of f of z dz along the contour c is equal to 0. And so that means this whole thing on the right hand side is equal to 0. So that means the integral from 0 to infinity of f of z dz is equal to I times integral from 0 to infinity of f of iz dz. So that is what we get here. And notice that the I times f of iz is equal to this thing right here. And so see, this is similar to the integrand of our original integral that we're solving. So well, plug in the expression for f of z and I times f of iz, and changing the dummy variable for the integration to from z to x, then we get this equation here. The variable doesn't matter, we can use z or x, whatever we want. So the integral from 0 to infinity of 1 over x to the fourth power plus 4x cubed plus 7x squared plus 6x plus 3 dx is equal to the integral from 0 to infinity of, well, I times f of iz is this whole expression, so is equal to the integral from 0 to infinity of 6x minus 4x cubed plus I times x to the fourth minus 4x squared plus 3 over x to the fourth minus 7x squared plus 3 in parentheses squared plus 6x minus 4x cubed in parentheses squared dx. And so we get this equation. And now let's take the real part of both sides. So we will neglect the imaginary part here. So let's take the real part of both sides and we get this. Alright, we get this equation here. So the integral from 0 to infinity of 6x minus 4x cubed over x to the fourth minus 7x squared plus 3 in parentheses squared plus 6x minus 4x cubed in parentheses squared dx is equal to the integral from 0 to infinity of 1 over x to the fourth minus 4x cubed, not minus, plus x to the fourth plus 4x cubed plus 7x squared plus 6x plus 3 dx. That's quite long, but so, well, notice here in the numerator we have 6x minus 4x cubed, and we just need to divide it by 2 to get 3x minus 2x cubed, which is exactly the same as the original integrand of the integral that we're solving in this video. Alright, so now we need to solve for this integral. And then we just need to divide it by 2. And we get the answer for the original integral. But to solve for this, we need to solve for this integral first. And notice that this fourth degree polynomial in the denominator, it can be factored out as x squared plus x plus 1 times x squared plus 3x plus 3. And well, now we know its factorization. So we can do partial fraction decomposition. Or, well, remember that I told you that you can verify that f of z has no pole inside C by finding the poles of f of z, and well, we can find the poles of f of z by finding the zeros of the denominator of f of z, and we know that the denominator of f of z can be factored into these two quadratic polynomials, so it shouldn't be hard to find the zeros. So it shouldn't be hard to find the poles of f of z and to verify that f of z has no pole inside the contour C. Alright, so let's get back to this evaluation of the integral here. So, well, we can do partial fraction decomposition. So we get this integral is equal to 1/2 times the integral from 0 to infinity of x plus 2 over x squared plus 3x plus 3 dx minus 1/2 times the integral from 0 to infinity of x over x squared plus x plus 1 dx. And these two integrals shouldn't be hard to evaluate. It should be easy to evaluate. It's just some basic calculus. And so we get the result is pi times square root of 3 over 12 minus natural log of 3 over 4. So this is the result for this integral, and we're gonna substitute this into this equation and we get the result for this integral. Alright, so we get the integral from 0 to infinity of 6x minus 4x cubed over x to the fourth minus 7x squared plus 3 in parentheses squared plus 6x minus 4x cubed in parentheses squared dx is equal to pi times square root of 3 over 12 minus natural log of 3 over 4. And now dividing both sides by 2, we get the integral from 0 to infinity of 3x minus 2x cubed. So we're dividing both sides by 2, so the numerator 6x minus 4x cubed divided by 2, so 3x minus 2x cubed over the x to the fourth minus 7x squared plus 3 in parentheses squared plus 6x minus 4x cubed in parentheses squared dx is equal to pi times square root of 3 over 12 minus natural log of 3 over 8. Phew. Well, this was a quite crazy integral, like just messing around with the contours and what function to choose and stuff like that. So I know it's not really intuitive at all, but it's quite fun to solve this kind of integrals. Anyway, thank you for watching.